let's make an additional example. Let's say we have two probabilities. PA is 0.3 and PB is 0.7. And let's ask a couple of questions. Can we compute P, A, and B? Can we compute this? Yes, no? Yes? No? No? Okay. Why yes and why no?
Because we don't know whether they are independent or not.
Okay. And you are saying?
They add one.
Say?
They add, assuming one. So yes.
Assuming they are independent, we can compute this? Yeah? And if A and B are independent, what's the result? Huh?
If they are independent,
Should be 0.
0.21.
0.21.
0.3 times
0.21, which is PA times PB. I should bring a dice. I have a coin, and let's assume we have a dice. What's the probability of tossing a heads with the coin and casting a 6? Probability for heads is 0.5. Probability for a 6 is 1/6. So is 1/12. 0.5 times 1/6. Right? That's the probability. Because apparently they are independent. The result of this one doesn't depend on this one. Okay. So let's assume they are independent and this is the answer. Yeah? If they are not independent, then no, we can't. Because when we look here at our earlier page, what is the result of PA? PA is 0.1 times 0.7 plus 0.9 times 0.1. That's the probability of A. These two have to be combined. That's the total probability of getting A. If we don't know about B. Yeah? If we know about B, then the probability of A is either this one or this one. You're looking confused.
Oh, it's
Okay,
okay.
good. Okay.
So basically, the probability of because of B, if they are independent, is the probability of right?
If the that's something.
I'm just looking to the formula on the right. So the probability of A and B, you can also write it as the probability of A.
Yeah.
Because of B.
We had this formula earlier that we were writing for conditional probabilities. The probability of A for some given B is the probability of both A and B divided by the probability of B, right? If we just rewrite this and say, okay, that's then PB, then we have here the probability of both is PB times PA given B. And now if A does not depend on B, then this is PA. Always, no matter B. And then we are back to the simple multiplication formula for independent probabilities. Okay. So assuming they are independent, this is A and B. What is if they are independent? What is the probability of A or B? Exactly. Yeah. If they are independent. And yeah, the other one. Now let's assume we are given an additional piece of information. Let's say we know PA and B is 0.1. What does this tell us? We know PA and we know PB, and this is also true. What now?
Then they are not independent.
Apparently, because we just computed if they are independent, PA and B needs to be 0.21. They are not independent. Okay? Exactly. So, let's see. Let's move to an example. So, let's see. Okay. Here, that's an example that automatically leads to these conditional probabilities. Let's say you have an urn that contains 100 balls. 70 of those are made from wood and 30 are from plastic. And 25 of the wooden balls are red and 45 are green, and 10 plastic balls are red and 20 are green. Yeah? So that's how we assign these two probabilities to the A and B event. And then we can come up with this contingency table here where we summarize all the probabilities. What is the probability that a ball is made, one of these 100 balls is made of wood? It's 70 out of 100. The probability of a wooden ball is 0.7. Yeah. Similarly, the probability of plastic, so that's a complement, is 30%. We also know the probability that we have a red ball. Yeah. That's 25 wooden balls and 10 plastic balls, so it's 35%. And we have for green 65%. And these are the combined A and B, A not and B probabilities, and so on. So that's written as a probability table, what we have here in this example. And this can be drawn as a tree diagram. If I randomly select a ball, that's the experiment, I have 70% chance to find a wooden ball, A, or 30% chance to find a plastic ball. And depending on whether it's a plastic or a wooden ball, we have different probabilities for its color. Yeah? These are these two probabilities that we don't know. What we know is we combined A and B naught and A and B probabilities. How do we compute this? How do we compute the probability of B given A? Ja, just einfach reinrufen.
You divide the probability of A and B by the probability of A.
Yeah, recall, this is the result of this probability times this probability. So if we divide this by this, we get this. Exactly. And the same can be done for all branches, all paths through our graph, basically. So if we do this, let's say B and A, yeah, so we have this result here, 5/14, and so on. And that means these are the conditional probabilities for our setup. Good. Let's see. Let's do this in on the tablet. Come up here with a better solution. Now let's look at an example that may be more related to what you do in astronomy.